Good morning, everyone. It is my pleasure to talk to you at this conference. I am Aslani, a PhD candidate working under the supervision of Professor Jorge Gascon. In this talk, I will show you how the Barracuda virtual reactor helps us to regulate the crude oil to chemical process in a multizone fluidized bed reactor. So the outline of this talk, first of all, I would like to introduce the crude oil to chemicals, and then I will briefly go over the elements that we are working on for this process, which are the catalyst and the reactor, followed by the ongoing work. So, what is crude to chemicals, or why we work on crude oil to chemicals? So, if you look over the global increments liquid demand from 2018 to 2035, focusing on the chemical sector, we can also see the liquid fractions, and we can show the demand of the liquid fractions using squares. So if it is green, that means it's growing high, and if it is red, it's declining. So overall, we can see that most of the demand is growing in the chemical sector compared to other sectors. Looking at the total demand for each liquid fraction, also we can see that the lowest ones are the heaviest fraction. So regarding the different sectors, we can see that we don't need or there is a declining demand for the power generation. So the chemical sector is the greatest sector. Let's say that it has, or one of the greatest sectors that demand the liquid. So how are we going to convert crude oil? We are following the direct catalytic cracking approach, where we convert the Arabian light crude oil into olefins and aromatics, which are the basic building blocks for the chemicals industry. So as I mentioned at the beginning, we are working on the catalyst. So we would like to have a catalyst that can tolerate the deactivation and spray. We can spray dry it in an efficient way. And also we would like to work on fluidized bed reactors for the reactor side. So that is due to the fast deactivation of the catalyst in this process. And in order to design those fluidized bed reactors, we need high throughput testing in the lab in order to get more data that will be used for the kinetic modeling. So it is not a trivial task. Let us go over the first element, which is the catalyst. So the composition of our catalyst is similar to that of fluid catalytic cracking. But the only difference is that we are incorporating the silicon carbide nanoparticles. So in this paper, we showed that our formulations share the same zeolite and binder composition. However, the difference is only in the silicon carbide nanoparticles. So one of them has the silicon carbide, which is the ACM101, the other does not have. So if we look to the right-hand side of this slide and focus on the right half of the figure, the top shows the ACM100 and the lower one shows the ACM101. So we can see that there is insignificant difference in the morphology after adding the silicon carbide nanoparticles. So in the other side of the figure, we can see that the particle size of the ACM101 is larger than the particle size of the SEM100 due to the incorporation of silicon carbide nanoparticles. So, and this leads us to the physical properties, to other physical properties. So, as we can see, the gendered classification, where the density of the particle, or the difference in the density of the particle and the density of the gas, is plot versus the particle size. So we are targeting the group A irritable region. So if we look to our formulation SM101, it has lower particle density, which could be attributed to the larger particle size and also higher porosity of the catalyst. And if we go to the other property, which is the thermal conductivity, so we can measure the thermal conductivity in the lab up to certain temperature. So we have two sets of data, one for the same CM101, and the other one is for the ECAT. But since we have linear trend, we can extrapolate those trends to our practical temperature in this process. So we can see the effect of adding the silicon carbide nanoparticles on enhancing the thermal conductivity of our catalyst. So regarding the tapping density, we can see that if we increase the content of silicon carbide nanoparticles, we are going to see higher tapping density, and also the size of those particles matters. So if you increase the size of the silicon carbide nanoparticles, the density will also increase till a certain region where we increase the size above 7 micrometer. We can see that we have lower bulk density, or tapping density, due to the destruction of the particle. So if we compare the catalytic cracking performance of our formulated catalyst versus the ECAT in terms of total gas yield, gasoline, propylene, and the coke. So our objective is to see which catalyst will lead us to higher conversion. So we performed the experiment in a reactor that we reported in Nature Catalysis paper. And we call that multizone fluidized bed reactor, where the crude oil is injected in the region that we call reaction region, and there is an upward stripping gas that takes the products to the top side of the reactor. So by fixing the shown conditions, we showed that the SM101 leads to more conversion. So this is in general about the catalyst. So if we go over to the reactor, here is our process workflow to reach the final design. So first of all, we propose a prototype, then we fabricate a reactor to do the cold flow experiments at room temperature with an inert gas, and out of this we measure the catalyst bed expansion. Also the same for the hot flow. We increase the temperature and we perform our reaction, and we measure the catalyst bed circulation and heat transfer. So coming back to the reactor, which was explained before. So here I will break that reactor into multiple zones. So the furnace is in the preheating zone with the lower heater, and the stripping gas is going upward. And then at the top of the stripping zone, we have one segment, one zone that's called the stripping zone. So now we have two heaters, top heater and lower heater. That means we can vary the temperature between those two zones. And then we have the reaction zone, and above that is the freeboard zone. So we collect the products from the top. So those are the thermocouples that we use for the one controlling the furnace and the one measuring the temperature inside the reactor. And we have the virtual flux planes that we are going to discuss more in the coming slides. So for the cold flow, this is the apparatus that we have in our lab. So we can see in this figure that we are monitoring the bed expansion versus different flow rates. And we have some experimental data points. And also we have predicted points from the Barracuda software and also from one of the simple models, which is the two-phase theory approximation. So we can see that the ones we are getting from the Barracuda almost match the experimental data. So this is one of the features that we are benefiting from the Barracuda virtual reactor. So here I will show you some videos regarding the hot flow. So where we have the reaction temperature at which we are heating the wall. And so we can see the red lines indicating the height of the catalyst bed. So if we start the simulation, we can see that the effective bed height for the SM101 is going higher and higher, while for the one for the ECAT is going lower. And this is due to that our catalyst SM101 has higher tapping density. So this is one of the advantages for this, in addition to the narrow particle size distribution of SM101. So in the case of ECAT, you can see the fines. And here we are utilizing the feature that we can enlarge the particles in order to see them clearly. And also, in the same time, we can look to the other parameters that are used for the optimizing the fluidization, which are the maldistribution factor and the slip velocity. And here we are utilizing the feature of having flux planes. So based on this data, we can see if there is a sudden change in one of those parameters, and based on that we optimize our process. So here again we are showing the flux planes. So we are here targeting the mass of the particle that is crossing up and crossing down those planes. So also in the right you can see that the black color represents the SM101 and the red color represents the ECAT. And we can see that since we have lower particle density for the SM101, so we have more gas solid mixing. So, and also it is shown in the graphs on the right, especially for the middle one. And also we can talk about the heat transfer, since we mentioned the thermal conductivity. So also this is one of the features in Barracuda that we have. They call it transient data points, where we can collect data points about the fluid temperature, the particle temperature. So we have two heating sources. the first heat source is the upward stripping gas, and the other one is the wall of the furnace. So, and the black color here represents the particle, while the red represents the fluid. So we can see that at the beginning, see that the temperature of the ECAT at this point is getting a little bit higher than for the one of SM101, and that is due to the lower thermal conductivity. So the heat cannot dissipate easily from the ECAT. But once the fluid temperature is equilibrated, and then we are starting, the wall start to heat up the catalyst particles, we can see that the SM101 is reaching higher temperature at this point over the ECAT. So, and this is now because of the higher thermal conductivity and also the efficient heat transfer. So finally, I am going to show you some of our ongoing work. So coming back to our workflow, after we finish studying the hot flow, we are studying the chemistry of the crude oil catalytic cracking. So in which we are targeting a kinetic model that can be coupled with our hot flow simulation and also can be validated with the experimental data that we have. And then further we go to improve the reactor design, condition, optimization, etc. And after that, by the end, we can go to scaling up in the demonstration unit. So in order to get the chemistry, so there are two approaches. The first approach is the microactivity testing, which is the standard way of getting the kinetics of fast deactivating processes. So for the main advantage, or let's say the main drawback or disadvantage of this MAT reactor, that the gas and solid residence times are different. Other advantages like good mass balance for heavy feed, in situ coke measurement, that means we don't need to take off the catalyst after each and every experiment, and we can do multiple experiments per day. But on the other side, we are also working on the Berti reactor. So the main advantage is that we have same gas and solid residence time. But if you look to the different configurations, especially the lower part representing the Berti reactors, so we have an impeller rotating. So this is the main difference between this type of reactor and the MAT. For example, the MAT is the continuous one, but without an impeller and with outlet from the bottom, let's say. But also for the Berti reactors, it could be the bed could be fixed or fluidized. So of course we are going for the fluidized one. And our goal in developing the Berti reactor with ILS company is to have a setup that can represent the Berti reactor and at the same time can have the good features of the microactivity testing. So in order to simulate the Berti reactor, we have two approaches. The first approach is the computational fluid dynamics, where we can model one part of the reactor instead of the whole reactor, and also we can represent the particles by porous media, fixed porous media. And also we can simulate the rotation of the impeller in order to get the gas velocity. And in this case, we use the ANSYS fluid. But for the other, which is the one we are talking about today, is the computational particle fluid dynamics, where we can study the gas-particle interaction using a Barracuda virtual reactor. And the general, say scheme about those two approaches, the inputs are almost the same, but what we are getting from the computational fluid dynamics is mainly the bit velocity, especially at different impeller rotations. While in the computational particle fluid dynamics, we are looking for the bit expansion. So in order to integrate those two approaches, so what has been done in this study, that the bit velocity was taken from the CFD and was included in the boundary conditions in CPFD. And then after solving or running the simulation, we get the new bit expansion and we update the mesh model, especially the porous media model, based on the porosity and the height of the catalyst bed. And then again we iterate with the so taking in consideration the pressure drop and contact time among the two simulations. So this is in general our flow using the Barracuda virtual reactor in our research. So it's my pleasure again to talk to you, and you can refer to our publications that I just mentioned for more details. And thank you very much.